Is it visible to everyone? Okay, great. So today I'll cover the autoencoder, and in the first morning session, and then in the evening session, I'll go for the demo part, uh, what I told, what we discussed last time. So this is like, we can say, this is more or less the last chapter that we are going to cover here, and then our course will be completed. Okay, so let's begin. In machine learning, uh, till now what we have seen, so most of the techniques which we have seen, those were like related to supervised learning, because we were having the labels. So whenever I'm saying supervised learning, that means we are having the labels, or like labels or target labels, and our goal is to map from input to labels. So what we were doing, we were having we were designing the architecture. It was taking the input x, and then it were giving some label like class, and then we had the ground truth, that is the actual labels. We were also knowing about the actual labels of this act, and with the help of the actual labels, we were finding the loss here, and then it was getting back propagated. So this type of setup is called supervised setup, because you are supervising this output, or this model, based on the target labels, because you are aware of that target, you are having that information. Okay, and the goal of this uh, part is to learn the mapping. It's like some sort of function that you are going to learn here. So this function will map the x from x to y. Y is your label. Okay, and this is being used for supervised learning is being used for classification. Like, it's like a lot of examples are there for this type of learning, like classification, regressions. These are the examples of supervised learning. So like I told you that we are having the, for each image, like if you're dealing with the images, then we have, for each image we have corresponding labels also attached with that, like this dog, this cat, and and so on. Okay, now coming to the unsupervised. So in the case of unsupervised learning, uh, target class or labels are not provided. That means you are not having the this pair. I'm just giving you the image, not the class. So that label information is not there with you. It's like, whenever I'm telling, whenever I'm telling this thing, this setup is for the training. Okay, because you are going to train your model, and that's why the learning is involved. So whenever you are going to learn, whenever your model is going to learn, then these are the things which are like, then only like these are the meaningful terms. For the testing, no need to see like what supervised, unsupervised is fine. Only for the training, if we are having the labels along with the image, then you can say, hey, this is supervised learning. If you are not having labels along with, we are having the images, we are having the samples, but labels of all those samples are not uh, provided, then you can say, hey, this is like, here we have to apply unsupervised learning. So if there is no label target class, then again we have to somehow fetch, or from the samples. So in this case, we generally try to learn the structure of the data. Okay, so in the unsupervised learning, since you do not have the labels, so you cannot go with the method which we have, which we were using in this case, like cross entropy loss, or, so because you do not have the labels. So how should we, uh, how can we find the loss? So for getting the loss, you should be having actual labels also, but that is not there in this case. So here we could be having different type of strategy. Again, goal is to learn the structure from the data. Here also the goal was to learn the structure from the data, but here you were reaching to the final goal, final class level, because you were having that, those all the information available, and that's why you're directly moving to the class. But in this case, you do not have class information. Again, Again, in this case also we need to learn something, and that is the structure of the data. Okay, and for learning this, for this type of data set, we have different type of algorithms, which are like unsupervised based algorithm, and those are like k-means, PCA, etc. So using these algorithms, you can find the cluster of uh, different sets from the data sets. Maybe one set could give you one class like that. Okay. So here also, like in unsupervised learning, our goal is to find find the different sets which can be differentiated by some boundary. So like this, suppose you in your data, suppose you are having this a lot of circles and a lot of maybe additions sign. Then if you apply unsupervised algorithm, then maybe after doing applying that, like once your learning is done, then maybe at the end you could be having this type of cluster. Maybe this is one cluster, this could be another cluster. So similar type of samples would be given to the one cluster, and dissimilar type of samples would be given to the different. So it should happen. So we are somehow trying to learn the things from the structure of the data. Okay. Okay, so even in this case also you could be having the problem or related to classification, but since we do not have the labels, so based on the structure, based on the information given in the data, can we can we find different cluster, and then can we say like one cluster as a one class? So that can be done here. Okay, so this is like one application of this unsupervised. Even unsupervised based learning also can be used for the classification, for solving the classification problem, but not in a direct manner. Indirectly, you have to find the discriminative, like you have to differentiate this thing into different cluster. You have to find different cluster, and then at the end we can say, hey, one cluster is one cluster belongs to one class. Okay, uh, so this autoencoder comes in this unsupervised learning paradigm. So whatever unsupervised, what like if you have once unsupervised based of goal, unsupervised based of learning, then you could apply some traditional techniques like PCA or all those like k-means. But even in the deep learning, we have autoencoder, which can be which can be used, which can you can use that for solving unsupervised or for the unsupervised based of learning. So whenever you have the problem related to unsupervised based learning, then you can also use autoencoder. Now let's understand what is autoencoder. So if I show you the autoencoder structure, so we are having this type of structure of the autoencoder. So we have encoder part, and then we have decoder part. Now goal is it is autoencoder. So now this name itself says like whatever input I am giving to this encoder, I expect the same output from the decoder. So I'm giving X, I want X dash from the decoder. And what is happening here? Encoder is having a set of layers. It could be any type of layers, like fully connected layers, CNN layers. You can use any type of layers. And what it is doing, it is uh, like making this X to Z, like robust representation. So it started with the X, and now making the like it's like higher dimensional space. We have a lot of values here, and now we are making doing the compression. Okay, so after this applying the encoder, you got the compressed feature representation, that is it. So we are saying this thing as a robust feature, and it is coming from the encoder part. So after applying a certain layers here, that will give you Z. And then what we are uh, doing, like we're taking this Z from here and giving to the decoder and telling to decoder, hey, you reconstruct the same X, what was shown to encoder. So goal is to generate X dash. So it should be similar to X. And again, since you know that at the starting, everything will be not in your side. Okay, so you'll be not getting very good result. Maybe you could be getting very bad result. So then you have the loss. You can apply the loss function between x dash and x, because your ground truth is x only, because you are going to generate the same image from the given image. So whatever image you have given to you, you are going to generate the same image from this encoder decoder setup. Okay. So maybe you can apply Euclidean loss here, or maybe L1 loss here, find the difference, and then go back and train it. Do the back propagation. And let me just tell you, this encoder decoder is not the separate. It's not the separate network. It's like combined network in a single box. So we have like one. This is like first part. This is second part, and they are connected. Here they are connected, so that like if you go back in the back propagation, loss will be back propagated till end, like till the starting point here. Okay, so this is the setup. Once your training is done, that means your encoder decoder has learned that mapping. So after learning, after training, now it will start to give you whatever x you are giving here. It will start to give you the similar uh, output, very similar output. Okay, because you have like trained this thing for doing the same. This is your autoencode. It's very simple architecture. Now you could also ask like, hey, what type of things I should use? And I already told you that any type of network you can use here. But in many cases, what we do, we generally like even CNN. If you're applying CNN or even fully connected, we try to downsample the image, try to reduce the size of the actual image. Okay, so that at this point we'll be having only the robust, only the information which are like very important, and that would be given to this second part, and that will give you the same image from that. Okay, now let's give the answer for this question. The first thing is, if I ask question, hey, why do we need this dimensionality reduction? Why we are doing this? Why we are making this setup? That would be the my question. Why we are making this setup? Since I'm saying, hey, make the reconstruct the x from the x only. Oh, we already have x given the data set. We have the data set, and I'm picking the x from here, giving to the model, giving to this network, and then saying, hey, you reconstruct the same x. So what is the meaning of this? Because we already have this x. Why to reconstruct it again? So I think in that case it would be not helpful. Then why we are doing it? The answer would be the first answer. Like there are multiple applications. So maybe first applications would be maybe encoding, decoding. So whenever you even when you use the internet, like when you send the message maybe on WhatsApp, so what you do, like you type the message, and then your message will not go in that form. Whatever you are typing, it will not go in that form. What is happening inside the the functions or the algorithms what we have in that this computer network or in internet, what it will do, it will encode that information so that other cannot uh, get that information, because it should be like it is private to you. So whatever information you are sending, other guys cannot, should not see it. In between whom you are sending to this, that guy will be able to see it, but in between a lot of nodes are there, a lot of guys are there, they should not see this. Okay, so if you send in the same form, then it's there's chance that other guys can also see it. So what we do, we generally encode it. So traditional, like we were using, if you just see, people are using traditional approach to encode it. It's part of can say cryptography, like encryption, decryption. So encrypt it, and then receiver side you can decrypt it. In this case, here it can be also used for doing the same. So what you can do, we can take, we can train it. We have trained this x to x transformation, and then keep this encoder part on the sender side. So whoever is going to send it, that guy is having the encoder. and it will give the X to that encoder, that message to the encoder, and encoder will give the representation from that. And then this will be sent to the receiver side. Now, other guys, if in between any guy, if they see this, they'll be not able to interpret it because it's not in an actual form. It's like transform form, encrypted form. Okay, and now this will be received on the receiver side. Now, what receiver does? It takes it, and that receiver would be having the decoder. So it will take the decoder, and it will. So this is Z. So Z will be sent to the decoder side, this receiver side, and receiver will take the Z, and that receiver is having this decoder. So after training this, once your model is this whole architecture is being trained, then you keep this encoder part on the sender side and keep the this decoder part on the receiver side. Now receiver will take the Z which it got from the sender and will give to the decoder, and decoder will reconstruct the actual message. So this is one application where it can be used. Let's go for some other applications. Maybe sometimes like you might have used some dimensionality reduction method. Sometimes we need to reduce the dimension. So maybe you might have used PCA, LDA, principal component analysis, then LDA. These are like dimension. These are the methods for dimensionality reduction. Sometimes we need it because of it could be due to the noises in the input, or maybe due to uh, the 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 limitations of the system. Like if you have very large input, then again if you're applying some method, it could be having very large complexity. So maybe for decreasing the complexity, you could use PCA, LDA. Even sometimes in the original input, you could be having a lot of noises also. So after applying the PCA and these all those feature reduction technique, they will reduce the feature and keep the main features there. So even in that case also you can use this autoencoder. And autoencoder would be better than that PCA and LDA in most of the cases. Why? Because in autoencoder it is like non-linear type of functions that we are using here, because in this encoder part or decoder part, everywhere we are having a lot of different layers, and in every layer we could be having some nonlinear function like ReLU or any type of nonlinear function. So this whole setup is having the nonlinearity. But if you just go with PCA, PCA is like linear function. So there, like PCA will not help you uh, uh, in a great manner when we have very complex problem. But in that case, autoencoder could be helpful. So even in that case also you can use. So that second application is like feature reduction. Now third application, let's see the again one more application. Uh, you can also use this in autoencoder for doing the classification. Suppose I have given you the data set, and in that data set, you are having a lot of images, lot of samples. I'm telling you, hey, you train it. You train this model for doing the classification. Okay. I have given you a lot of samples. But the thing is, we have only few labeled samples because I do not have uh, uh, that much time, or I am not having that big group which can label every image. So that's why like I have given you some labeled image, but most of the samples are not labeled. So in that case, if you're going to train your model, you know that your model would be either overfitted or underfitted because of limited data, because of limited label data. So you are going to learn this model, and uh, you want to have a model which would take X and will give you Y. This is the model that you want. Like take the input, take the sample, take the image, and give the label. They give the class for that. But the thing is, this paired data, you have only limited number of samples in this for this paired for this label data. Okay, so label data, I'm giving you some label data, but I'm having a lot of unlabeled samples in that data set. Okay, so maybe 3 by 4 parts are like unlabeled, where we are I'm not providing you the label. I'm giving you the images, but not giving you the class for that. But maybe 1 by 4 is like where I'm giving both the things, like paired, x y paired. Okay, so if so for this part there is no problem, because you want this part, you want this, so that you can learn this, your model can learn this mapping. But the thing is, this part is it is having very less number of samples. So in this case, what you can do, maybe since you know that you have a lot of unlabeled data, so use this part also, take it and learn the autoencoder, because at least you are not having label, but you know that you have the model which can learn, which can go with the this unsupervised learning. Hey, why I'm saying autoencoder as unsupervised learning? Because I'm not providing the label. You already have seen that we are going from x to x. That's all. You're not giving any class label here, and that's why this is like unsupervised learning setup. So whenever you are not providing label, that setup is called unsupervised setup. Label means your class, or maybe the actual regression value that you want to get from the model. So here in this case, you're not doing anything. You're just giving whatever input you are giving. You are expecting the same thing as the output. That's why you're not giving any label, any ground truth to it. Okay, but you know that since I have this structure, I have this model, I have this autoencoder setup, which can be used for unlabeled data. So why not train it? So give the unlabeled data, all 3 by 4 data, and train it. So at least it will learn the structure, it will learn the information structure from the data. So once it is done, then maybe your encoder part will be uh, helpful for you, because encoder part is what it is doing. It is taking x and giving you z. Now you know that this z is coming from the x only, and from z again you are going to the x dash. You're going to the x dash. That means this z is very powerful. It's very robust. Why? Because that's why your model is getting z, and again it's reprojecting to the x. So in this z we have all those information related to x. Otherwise it will be not possible to again regenerate the x. But if you are able to get it, that means your z is containing all those important information which are required for getting x. And it is having very low, very less noise, because we already have filtered it through multiple layers in the encoders. So then after training this, why not we use the encoder for, for doing the classification? So even if you see the classification type of model, you could be having something similar to the encoder type of structure. I started from the original image, reducing, finally reaching to somewhere maybe with small level of features, a small size of features, and then giving to the classifier and doing the classification. This was happening in the case of classification also, like whatever structure we have seen before. So here what we do, we take this part and then we add one classifier after this, because this encoder is not doing the classification, it's just doing the feature reduction. Now take this and add one classifier after this, like one another fully connected layer, and then do the classification. Now for again you train it, but you don't train this part. Even you can also train it, but at the starting you should not train this part, because it is already trained on this data set, on the same data set, and it has already learned this transformation, like going from x to z, and you know that z is very powerful. So why should I train it this part? So don't train this part, only train the layers which you have added after this. That is for doing the classification. And for this, you have at least 1 by 4 data there. You use it. So whatever supervised, whatever label data you have, you use it and train it in a supervised manner. So what's the idea? Idea is like first you train this thing in an unsupervised manner, and then you train it for the supervised manner. And this works. Even when I was also doing it, like when I was actually in my research, I also tried it, and it worked very well. Maybe 2-3% improvement would be there, even more than that. So you can try it. Like sometimes you can try it. Even if this is not working, then you can think about some other things. But in some cases, it will work. Okay. So I have already. Okay. So you can see like maybe if I'm giving you image MNIST data set, and if I say you hey train it, I'm not giving you the labels. And if I'm saying hey train it in an unsupervised manner, so what will do? You'll take the one like set of image, give to the model, and expect the same images as output, and then find the difference and then do the back propagation. Once it is being learned, then maybe your model, because you know that this Z, whenever you are going from X to Z, this X to Z and again Z to X. Now this Z is, we can say in other words, I can say, hey, this Z is having the discriminative features. That's why your decoder is able to generate the same image from this. Otherwise, it would be not able to do it. So Z is having the distinct or maybe what we say most important information of each image which you are giving to the encoder. And that's why I said, hey, you can also use this part for doing the classification, because Z is giving you already different feature for different X. And that's the beauty. And again, in the classification, what we want to do, we are doing the same. We want to get the discriminative features at the end so that it can do the classification in a proper manner, in an appropriate class. And similar thing is happening here. So you can use it. Okay. So after applying this encoder decoder structure on the MNIST database, MNIST, you know that we have handwritten digits, but we are not providing you the labels. I'm just giving you the images and then telling you, hey, you learn this autoencoder setup. And once it is done, just take the encoder part, give every image from the MNIST data set, and get the Z. And then you plot it. Just see like whether you are getting different cluster or not. So if you plot it, you might be getting this type of clusters. Like maybe one, suppose zero is going maybe here. All the zeros, all the images which are having digit zero, they are very close here and making one cluster. Then maybe this blue is like 7. So in this manner, you can see like we are getting cluster for each digit. Why? Because they are very close, and they should be, because in the image space also they are close. So in the feature space they should be. And this can be, even if you're not having class, it can be used. You can make the different cluster, and then one cluster can be it can be work as a one class, and then you can also do the classification using this. These are the some of the examples. I'm not going to. I already have explained it. Okay. So what I said that you can use autoencoder for just for the pre-training. Even if you're going to solve the classification problem, first you pre-trained it, like train the autoencoder setup, remove the decoder part. After training, you remove the decoder part and take the encoder part and then add the classifier, few more layers, and then do the. So this encoder can be used, it can be seen as a feature extractor. It's giving you the best feature from the input. We could be having other type of applications also. There we are not going from same image to same image. So when you are going from same image to same image, that is called autoencoder setup, because auto means same to same. But this setup can be used for other type of task also. And those tasks are like image, the semantic segmentation, high resolution, low to high resolution, image to depth map. A huge number of applications are there where you can use this setup. And even in this encoder decoder setup, you have seen in the transformer also. So you can see like how much popularity it is having. So this is like very good structure, and people try to use this at multiple places for solving a lot of different type of problems. So we'll just go through some of the applications, and then try to wind up. So semantic segmentation is the problem where we have given the image, and your goal is to segment it into like multiple parts. So it will give the different color to the different objects. So maybe you can say, hey, this first dog is giving this color, this is second dog is giving cat. So it's like first one is maybe dog, second one is cat, so cat is giving this color. And then we have some background also, so background is giving some other color. So in this manner, like it's giving, or maybe this part is also slightly different, so its part is giving. So it's like differentiating the different part, giving different color to the different part of the image. So it's just like clustering different objects in the image. So you can see here in this example also, we have RGB image, and then every object as well as the this background, all those things got clustered here. So different color. So here again, you can say this is the encoder. They have this is the paper which in that is Segnet, and that paper they have used convolutional encoder decoder. So in the encoder they have taken a lot of convolution layer along with the pooling layer. So they are reducing the size of the image using the pooling layer. You all already know like what is pooling layer. Now, so in this side, you are reducing the size of the image, and then this is the decoder side. This is the encoder side. This is the decoder side. So in the decoder side, you have to upsample it. So in the decoder side, they are taking this image as an input, and then it's like the size is getting increased by the layers. So for that, it's using the upsampling layer. So that's the thing. Hmm. Now, how should we do upsampling? So there are multiple methods. So downsampling, like when I was talking about downsampling, so what we have seen that if you have given the four things like 4, 1, 8, 9, then goal was to get one value. Like if we were applying the 2 by 2 filter over this pooling filter, then goal was like to, or if you are applying max filter, then you can take one value from it, and that would be your 9. And this is the output. So in that way, like you are reducing the size of the image. So from 4 to 1, this is the mapping from 4 to 1. Now in the upsampling part, because your goal is to increase the size, so there like will go in a reverse manner. So now the goal is to go from 1 to 4. Now how should I proceed it? So a lot of ideas would be given in different papers. The basic idea is, since when you are going from here to here, you'll be also saving the index, like from where it came, this 9. Okay. So you'll be also preserving that information. So while going back, now you know like what is the position of this 9. So you just keep that 9 there, and remaining values you'll just fill as a 0. Because this is the robust feature that you got from this, and now you are just preserving, you are just giving the robust feature at the particular position, and we are filling 0 to others. Again, you can ask like, hey, if I put 0 0 here, then it might make mistake, or maybe it could be not sufficient features, because we are losing the information here, because it came from here, but now we are not putting those values. uh, Instead we are putting 0 0 0. But again, we are not having only one layer. Even in the decoder side, we'll be having a lot of convolution layer. So those layers would learn, it will manage it. So pooling is just increasing the size, and then all the things will be managed by the convolution along with all those uh, non-linear layers, whatever layers we have, uh, whatever things we have in that block. Okay, so this is very basic idea, and we generally we use it, and it works very well. Another idea could be, or it already people already have used it. That is like you, since I know that this is the best feature that I got from these four values. So after going back, if you're going back, why not I should put this value everywhere? So in that 2 by 2 region, we'll put 9 everywhere. This is another idea. You can like you can try these all the things. Then even again, what I told you that since whatever you are doing here, since you have other layers also for managing it, and so you are somehow relying on the other layers also. So then also people came up with the idea like, why, hey, since I know that convolution layer is also playing the major role, because only this layer is not sufficient. After this, we have added a lot of convolution filters so that it will manage it, and it will give you the better features, better information from this. So then let us combine it in the pooling layer also. So they came up with transpose convolution, and that is like that is like this only, like mixing of upsampling and convolution filter. So they have just combined these two things in a single layer. So now transpose convolution would do the upsampling at the same time using convolution filter. So in this case, if you just see here, there is no learning, there is no parameter involved. In the pooling, there is no parameter involved. Even in the upsampling, since this is the fixed process, there is no parameter involved. Here also, there is no parameter involved. But when you go with the transpose convolution, transpose convolution layer, there the parameter is involved. So they have included the parameters even in the for doing this upsampling. So transpose convolution is like just you can see here, uh, going from one to, like, taking the few values, and maybe reaching to the this. So here, like, they have. So why not we learn it? So instead of just relying on the fixed uh, function for the upsampling, why not we should learn it? And they have used this transpose convolution, which give you the it will upsample the image, but here the parameters are involved. So we are learning the parameters for doing this upsampling. So I already have talked these all the things, types of upsampling, this all the things. Let's see one more application of this auto encoder. That is very famous, and that is called unit. This came in 2015, Mikai, and it's got very popular. And nowadays you can see a lot of huge number of citations are there for this paper, and still people use this type of setup at multiple places. So this is also encoder decoder setup. Uh, Again, one thing I forgot to tell you: autoencoder and encoder decoder. These are like two different things. Autoencoder, when I'm saying autoencoder, that means you are going from same x, you are going from x to z, and then again z to x dash. This is the transformation. If I'm saying encoder decoder, that is very generalized. In the encoder decoder setup, you can go from x to z, and again z to any p. Okay, so no need to go to the same x. And we have seen this example. We have seen one example for this. That is your semantic segmentation. So we are taking the image x, natural image x, and now you're going to z, and from z your decoder is going to the semantic map, not the original image. So this is more generalized. Encoder decoder is more generalized setup, which can be used for doing different type of transformation. It's not only x to x. So you can see, like, encoder decoder is like generalized version of autoencoder. Autoencoder is very specific, going from x to z, and again z to same x. Now let's come to the unit. So unit, it in that paper, it has been used for doing the this image segmentation. So, like, given the image, suppose if you have tumor in the suppose you have given the MRI image, medical image, and we are having some tumor in that image, how to segment it. So for that, unit has been used, and it has given a very promising result. And the idea was very simple. So it just taken the idea from the encoder decoder only. So setup was encoder decoder only. You can see here, encoder. This is the encoder part. This is the encoder part. and by every layer, your size image size is getting reduced. And this is the bottleneck layer, bottleneck where the like we can say after the encoder, whatever features you are getting, that's like bottleneck features or low dimensional features, and then it is given to the decoder side. And decoder is like reconstructing the semantic map, or we can say the segmentation map of this original image. Now, the the main part or the different part which was there in this case was this bypass route. This is called skip connection. So in the encoder decoder setup, if in the simple encoder decoder setup, this was not there. They have added it, and they found that this is giving very promising result compared to the state of arts. And why it is happening? Then they have given the justification and say, hey, what I'm doing, I'm passing the information, like suppose this and this, they are on the same level because they're having the same height and width. This and this, they're having the same level because they're having the same, because you have reduced, you started from the original image, then you reduce it, finally you reach here. Now this is the encoder. Now decoder will do the reverse thing. So it will start from here, again it will increase it, and finally it will reach the same size output. So now I can say, hey, this and this both are at the same level because they are having the same size. This and this, these two are having the same level because they are having the same size. Again, for this also the same thing will be applicable. So what was the idea? Idea was to pass the information from the left hand side. When I'm going from here to here, at this layer, at this part, on this part, we have the original image. And you know that in the original image, you have a lot of spatial information, because you can easily interpret, hey, these are the connect, these are the eyes, and why, and this is the nose, and why this is nose, because this is coming between those two eyes, and like that. Okay, so there's like relationship, proper spatial relationship that is there in this case. So that can be seen as a where information. So every, like where the informations are, those all the things are there. But when we are going below, your size is getting reduced. So you know that when you are going you are passing through different layers, your your image representation is getting reduced. So you started with very fine details information. It's just like going, first part is like seeing the earth from very close distance, but then we are going back. So that is the thing here happening. So when going back, maybe at the end you could be having global feature. You know, like this is, suppose if you take the example of earth, so you know that this is the earth, but you do not have the fine details of the earth. So you know, like this is the earth, that means you have the what information, but you do not have the where information in a proper manner. Why? Because you have lose that information. So by the layers you are losing the spatial information, but your, the main component or main information is getting preserved, and that is your global information. Okay, so you are losing the where information, but you are having the what information. Okay, and what you are saying to decoder, hey, you take this what information, maybe by reaching here you have lose a lot of where information. Now you are not having a lot of spatial relationship, you have lose that information. And then you are saying to this, we are just giving this information to the decoder side and saying, hey, you reconstruct the original image. That's a difficult problem. It's not easy problem. Again, you can say, hey, since we have the loss function, we know the ground truth here, then you can use it. That is fine. Okay, in this case, you are having the ground truth. So that's why autoencoder is like, when we are training the autoencoder, that is your unsupervised training. But when you are training the encoder decoder, this type of setup, then you have supervised training, because your P is different, and that P is the ground truth because you want to get this P. In this case, you are going from same X to same X. That's why like your ground truth was not required, because your goal was just to reconstruct same X. But in this case, your goal is to get the P, the semantic map. And for that, you have that image. And then you are comparing like how good your model is doing. And then you are finding the loss and going back. So that's why like this autoencoder is unsupervised way of training, unsupervised way of it's like method for the unsupervised learning. But encoder decoder, when I'm talking about the generalized structure, then that could be used for the supervised also. So this is the supervised way of training. Okay. So okay, now come to the main part where where we were. So we got the what information here, the global information, and then we are saying to the decoder, hey, reconstruct the semantic map. It's not the easy job. So it will try to do it. You find the loss, back propagation, but again, it's challenging problem. The idea of this paper was why not we help to the decoder. Since I know that decoder is having it got the what information in a proper manner. So it has got the what information. So for what is fine. It knows that hey, I have to reconstruct. I have to. I know that this is the thing, but it does not know how they are spatially connected because that information has been lost. Not fully, but most of the relationship, that spatial relationship has been lost because you are not seeing this thing from the very close distance. Now you are on the moon. So here you are on the moon and you are looking the earth. But you also want the find the structure like where this part is on the earth. That spatial information or where information would be sent from the encoder side. So this was the idea that what information is flowing here, then we can also pass where information from the left hand side so that it can help this decoder side to reconstruct the image in a better manner. So you can see at every level it's sending the information from this side. So maybe at this level you could be having a lot of spatial structure. At this level you could be having maybe little bit it's like not this much, but at least you'll be having some spatial structure. Here again you'll be having some spatial structure, but this side you are having not that much spatial structure because you have started from what only. From this side you have started from the where and the what both, but your what was not that much clear, but where was fully clear because everything was all the relationship was there. Now you have just filter out where. We are just removing the where, and we are just filtering out the what. And at the end, you left with the what, and then you are giving to the decoder. So the idea was just pass the where information from this side so that your decoder will get to know like how they are spatially connected, and based on that, it will do the segmentation. So at every level, we are just passing the information from the decoder side, encoder side. That's all. This is the idea, and they got very good results. So this can be used for like yes. So vision. All, this autoencoder has been used for solving multiple type of problems. So segnet, I already have told you. Image to map, then depth estimation again, molecular depth estimation. So even given the single image, can I predict depth map from the depth map means like it's required for generating the 3D image. So that's so this is also being used. Yeah, so here also we can use this auto encoder decoder type of structure, which can take the image and reconstruct the depth. Depth is like when you are going to reconstruct the 3D image, you need this depth. And in practice, uh, if you want to do it, you need at least two images from uh, from two different camera, and they are like equidistant, like they are at fixed distance. Or maybe you can take the image of the same object from different angle or from different side, and then you can reconstruct it. The 3D map of that, or this depth of the depth is like I can like even just looking the image, looking the thing, I can say, hey, how far it is from the part. So we can differentiate like even in the image when when you are taking the image from the your camera. So that is like those are like 2D images. So they're like if I say you, hey, how far these two objects are, you will be not able to tell. You will be not able to interpret it because you are not having the 3D information. But with the help of this 3D information, you can say, hey, these two objects are far they are like separated by this distance and like that. So that can be done using the 3D image. So even we have 3D image also. We are having the camera also which can give you the 3D image. But though they are like very costly, and that's why we generally find the cheap based method which can be which can help you without putting a lot of money. So this again, this deep learning idea could be helpful there, and people have used this for solving this approximating the depth from the image. So given the single image, how can I reconstruct the depth from that? And this already people have done it, and a lot of papers are there available there, and which can take the image and give you the depth map, and using this depth map you can reconstruct the 3D image. Just like our eyes, we are like habitual of seeing the 3D. So we are having two eyes, so that's what I'm saying, like two eyes are required, so two cameras are required at the fixed distance. And our eyes are also doing the same. It's taking the every eye is taking the 2D image, and then it's like both eyes are taking the 2D images, and then they are combining, making the 3D view of that. So in the similar, so that can be also done using the cameras, but if you go with the cameras on those, so complexity is more, cost will be also involved. So why not we should make the cheap method which can do the same. So even this deep learning can be used for reconstructing the for getting the depth map directly from the one single image, and a lot of works are there. Even for image super resolution, it can be used. So, given the low resolution image, like very low quality camera, if you're taking the image, how can we make the high resolution from that? So, this is again one type of application where you can use this or this encoder decoder setup. Then image synthesis, you can see here, like we are going from giving the low resolution image, and then encoder part is giving you the feature this Z, and then decoder part is converting it into the high resolution image. Then image synthesis also can be done, like from one type of image can I generate another type of image. So like this is one view of the image, one view of the scene. Can I generate another view? So this is maybe from one side it's looking like this, maybe from other side the same scene would be looking like a in a slightly different manner. So can we do it? So again, this type of works already have been done in the past. Okay, so with this, we have like completed this encoder decoder. Now my question would be here, like I'll just I'll allow you to speak, ask some question here. But before that, I'll just put one question here. Whatever I have told here, whatever I have shown here, uh, can I generate some new image from these type of setup? Even I'm just taking the autoencoder setup. So you are going from X to Z, and then again Z to X dash. But this X dash is coming from your data set only. So you have given the data set here. You have given the data set here, and you are taking the image from this X, taking the image from this data set and giving to this autoencoder, and your autoencoder is giving you X dash. But this X dash is not different than the images which you are having in this data set, because this X dash is, you're making this X dash similar to the X. But my question is, can I generate new image which is not there in this data set? Like my class, in this class, I'm having a lot of students who are like attending the class. Okay, now I take the image of every person, and then I make the data set. Okay, the face image of every person. And then what I'm saying, hey, I know that I can apply this autoencoder setup on these images. But then my natural question is, can I generate new face which does not exist in this data set or in my class? So is it possible using this autoencoder? This is the question that I have just thrown to you. Now, like I'll allow you to speak, and even you can also ask some question from the previous this topic encoder decoder, and along with, like, you can also give the answer of this. Yeah, please, you could give the answer. Tapaji, you were saying something.
So I was telling, sir, it can't generate the new image. It's the main features of autoencoder decoder is to reconstruct the image that as per the training data. So I
Yeah,
don't think it has the capability to generate a new, exactly new image. It
yeah,
might be like reconstructed one, but not the new face.
yeah. So then what should be the way by which we can generate? So what I'm saying that I'm giving X and getting X gas from Z. So your encoder is giving Z and then Z is given to the decoder and it's again giving the X dash. So what you said, like that's the very right answer. But then how should I generate it? Suppose I want to generate new image. I want new face which does not exist in our data set. So how should I do it? I know the images of my data set. I know all the face images of my class. I've just put in the one box. Now this is my data set. Now I can train the autoencoder from here. I can just train it. I can give the take one any x from here, give to the this setup and get the same x from there. Now
I
this
think that
yeah, please suggest.
Yeah, I think that sampling or shuffling can be one option. We can randomly select the vectors from the given
Hmm.
data set.
Hmm.
I'm just thinking, sir. Might not be
Yeah,
correct
yeah.
one.
I'm just yeah. You have to
or
just give the suggestion only.
dicing
Yeah.
or slicing and dicing of the images in the pre phase,
Slicing and dicing. What is this? Slicing means what?
like
It's like cut.
cropping,
Just
cropping,
patch.
rotation.
Okay, but in that manner also like because you are I don't think that it could generate new image because you are cropping the same image. Suppose I'm giving and cropping the image from here and giving to this encoder. Then again goal is to get the same image only. So whatever you are giving to the encoder with whatever input you are giving to this setup, it will give you the same, it will give you the similar type of image only, very similar image. That means almost almost the image which you have given in the data set. So I don't think in that case, even if, I'm not saying that this idea is it will not work, but I don't think that this will give you very accurate. It's like generative or new images. Okay, what is required for getting new image? Or maybe if I'm giving you this data set, so what should you learn so that you can give you new sample from this?
So redistributions of the data set, that might be the one option. So
Yes, that's the that's the only option. So you need to know the distribution. If you know the distribution of the data set, then you can generate any type of images because you know the mean and variance. And if you know the mean and variance, you can generate a lot of samples from that. Okay, that's the thing. Are we getting this? Okay, maybe here, which part is giving you uh, the image output as a image? Decoder part.
yes, sir, decoder part.
Sep- So I'll give. I'll just putting a lot of things here so that you will be able to realize it. Okay. So suppose I'm giving Z here and it's giving X dash. Now the thing is, I can change this Z. Instead of Z, maybe I can give Z1, Z2, Z3, Z4. And you know that for every Z, it will give you different image. So can I say, hey, I can use decoder as a generator. It can generate new image because I have the flexibility that I can choose any Z. Your answer would be, hey, this Z1, it's not coming from like it's not given by God. From where it's coming? This Z is coming from the encoder only. And what encoder is taking? The encoder is taking X as an input. So if I'm giving X1 as an input, your encoder will give you Z1. And then from that Z1 will be given to the decoder. And the decoder will give you the X1 dash. So now this X1 dash is not new image. And why you are not getting a new image? Because you are dependent on the encoder. And encoder will always take image from the database, from the data set. So only the main problem is your encoder. But if I remove the encoder, who will give the Z? That's the question. Because I want different jets. If I get different jets, I can generate a new image. Now, who will give you jet? That is again problem. So you cannot remove it. Then what? As one of you guys told that we have to use some distribution. Now, do I need? Can I will? Uh, is it possible to get the distribution of this data? Can I get the distribution of this data set? Is it possible? No. This because this image, this in this data set, you are having a lot of images, and they're having a very huge dimension. And due to that, it's not easy to guess the distribution of this data set because you're not having all the images of this data, all the images of this distribution. It's only few samples of that distribution, and you want to learn the distribution. So it's not easy. For this, it's not easy. So can we do it at this position, at the Z? Might be possible. Can I learn the distribution of Z? Because the thing is like we have to learn the distribution. We have to know like we have to if we understand the distribution of the X, then our problem is solved. But X is having very high dimensional things. It's like a lot of values. They are like all those dependent values are there. So that's why it's very difficult to get the distribution of this X. Now go to the Z because Z is having small number of features compared to the X. Can I get the distribution of Z? Even it's not easy job. But we want distribution of either X or Z. If you know the distribution of X, your problem is solved. You don't need autoencoder. You know the mean and variance of your system, your data set. You can generate any type of images from that. But it's very challenging. Let's try on the Z, but Z is not also is also not easy. Then what should we do? So we try, we make this whatever you are getting from E, you try to make this because you know that from like everywhere you are getting things from the some distribution only, but you are not aware of that distribution. So your E is giving values which will be like similar to some distribution, but you are not aware of that distribution. So then what should we do? We try to make this distribution similar to some non-distribution, some already well-known distribution. So you know that very easy distribution would be your Gaussian, normal like standard normal distribution, mean zero and variance I. So you take this zero I. This is your non-distribution that you know. This is your Gaussian distribution. So what we do, we tell them, we'll take the encoder decoder setup only. Okay. But in the case of in the previous case, I was not learning any distribution. What I was doing, I was just getting whatever X, whatever Z I was getting here, just giving to the decoder side and getting X dash. Now in this case, now since I want to generate new image, but in this setup you are not able to generate new image, then I have to change this setup. So what the idea? The idea is to make whatever distribution I am getting here because handling this is not very easy because this is having a lot of noises. In the original image, you will be having a lot of extra information. So I cannot handle this thing. So I may handle this thing more comfortably compared to this X. So work on that. So what I'll do, I'll tell the encoder, hey, encoder, you should give instead of giving Z, you should give the distribution. And I'll make that distribution of I'll make this distribution, whatever distribution I'm getting from the encoder, I'll make this distribution similar to the normal distribution. And if I'm able to do it, then my problem is solved. And this is already done. And this setup is called variational autoencoder. So I'll not go into depth because this is not part of it's like part of the generative AI. So like generative models. So it's like initial generative models. Uh, so VAE come up with that idea. So let's see VAE. just in a brief, maybe I'll take 5 minutes and I'll complete it. So VAE is just so VAE is this. It has just changed the setup. So X you are giving here. Now this VAE would be given you this is like encoder part. So encoder part will give you. So previously it was giving X to Z and Z to X. This was encoder. This was decoder. Encoder decoder. Now I'm saying to encoder to give me the distribution. So it will, instead of Z, it will give me mu Z, like distribution of the Z, like mu and maybe variance. So now I want these two things from the encoder, and then I am having the decoder. I'm having the decoder. I'll sample from this. So you know the formula. So I'll make the Z from this. So that is mu Z plus eta of sigma 2, or maybe this will be standard deviation. So this will be like root of, if I'm taking this as a variance, then the root of this. And this is the like this is very standard formula. So I'll make this Z from this distribution, and then we'll give that Z to the decoder. And decoder will generate the same X dash. Now in this case, what I'll tell to encoder, hey encoder, whatever distribution you are giving here, you are giving the distribution. You're giving the distribution of the Z. That's why you're giving mean and variance. Now you have to make your distribution similar to the normal distribution, standard normal distribution or Gaussian distribution. So I'll make this distribution similar to the Gaussian distribution. Now how to find this? Because this would be also one loss, because we have to match it. We have to force it to become close to the normal distribution. So finding the difference between two distribution, because this is one distribution and another is your normal distribution. Now I have to find the distance between this distribution and the normal distribution, and we have to minimize it. So for this, we have a function, we have method that is called KL divergence, KLD. So this KL divergence will give you the distance between two distribution. So first loss will be applied over this between the distribution that you are getting from the encoder and the normal distribution. And second loss would be the same, what we have seen before, that is X minus X dash. Because at the same time, it also has to generate the image. It has to learn the distribution, but it also has to generate the image. So from X to X dash, you are going. Now you are saying encoder, hey, you learn the distribution close to the normal distribution. And at the same time, you are also saying to the decoder, hey, you generate the image, same image from this Z. So both the losses are important. The generation along with the learning the distribution. Suppose it is being done. So everything is done. More training is done. Can I use it for generating new sample? You can give the answer for this. Hey, you got the stuff. Can you hear me?
Yes, sir. Yes, sir.
Yes, yes.
Yeah, yes.
So yeah, what I said that suppose my training is done and your encoder started to give you the distribution close to the normal distribution. So that was the focus. And decoder also, it is also giving you the image. Now after training, can I generate new image? Hey, your training is happening based on two losses. One is your x this loss, and one is like KL divergence between your the distribution that you are getting from the encoder, that is like mu2 and sigma mu and mu z and sigma z, and then you are applying KL divergence between this first distribution mu z and sigma z and comma this normal distribution, and this should be minimized, like distance should be minimized, plus this should be also minimized. So at the time you are having two losses. One is for generating the image, and one is for making the distribution of the encoder close to the normal distribution. Suppose it is done. Now can I generate new image?
So logically, yes, it should generate.
How? How? That's the question. You are giving x, you are getting mu z, you are getting sigma z, then you are sampling the z from this mu2 plus eta of sigma z. You are getting the z, and then we are giving to the this z to the decoder. That's the thing. And decoder is generating the X dash. Now, can I generate new image? You could give like you can don't do it like you can give in whatever answers are coming in your mind. You just put it here. Like, hey, with this setup, can I generate the image? With this setup, you're giving X.
We need some polling. I mean, that you are telling now. First layer give you the first layer, that type of thing. Information.
Your encoder is giving you mu z and sigma z. That is the distribution you are getting from here, and then you are taking the sample using that distribution using this formula, and then that z that you have got from that distribution you are giving to the decoder, and decoder is reconstructing the same image what we have given here. But so with this setup, are we able to generate new image?
No, no, sir. I think it's
No.
again it's reconstructing it. X dash is the
Yeah.
reconstructed image. It's not the new one.
Yes, that's right. That's right. So what should I change it in this setup? Hey, can I
If
go
we,
with only decoder part? Can I
if
go
we
with only
modify
decoder?
the distribution, then we can.
No, can I go with the decoder part? Only decoder part. In the case of autoencoder, it was not possible because your Z was coming from the encoder. That's why we were needed encoder also for getting the Z so that we can give that Z to the decoder and get the image. Now, can I remove the encoder part in this setup in this variational? This is called variational autoencoder. So, can I remove this encoder part in the variational autoencoder? Very natural question. Hey, after training, what you'll be getting from this setup? Can you tell me? After training, what will happen with this setup? What will happen with this setup? What was the focus? If I ask you about this distribution, mu z and mu sigma z, what you can say about this? What should be the distribution of this? Can you tell like what should be the distribution of this? Can I know the distribution of this? Hey, what we were doing using KL divergence? Just recall it. What your KL divergence was doing? It was making this distribution similar to what distribution?
Gaussian or normalized distribution.
Standard normal distribution or Gaussian distribution. So after training, what would be the type of this distribution? If everything is okay, then what would be? Can you guess the distribution of this? Yeah, give the answer. Hey, can I say like this will also follow the Gaussian distribution?
No, I think it will be more like ReLU function.
No. Your focus was to make this distribution. This is the distribution that you are getting, mu and sigma. And then you have applied the loss function over this. And what was the loss function? That loss function was the KL divergence between the distribution that you got from the encoder and the distribution and the normal distribution, standard normal distribution. So now you're minimizing this distance. So once your training is done, what will happen? This distribution will follow this distribution because this is the ground truth. This is the ground truth distribution that you want. And this is the predicted distribution that you are getting from the encoder. And you are making your predicted distribution similar to the ground truth distribution using the scale divergence loss. You're minimizing it. Your training is happening now. So you minimize this loss also. You're also minimizing the reconstruction loss. You're also minimizing this loss. So after some time, what will happen? This distribution, whatever things you are getting from the encoder, the distribution of that will follow the normal distribution. Is it right?
Yes, sir. Yes, sir. Got it, sir.
Got it. So if now can you say like what is the distribution of this? Can you say like what is the distribution of the this mu and sigma?
It is close to Gaussian.
It is close to Gaussian, and in best case, it will perfectly match with the Gaussian. So if I know that this is following the Gaussian, then why should I take this E? Since I know the distribution of the Gaussian, so in that case, I can directly take the sample from the Gaussian distribution. So now your encoder is not required. You can remove the encoder. Now I know the distribution of the encoder because it has like now it started to follow the Gaussian distribution. So now I'll take what I'll do. I'm having the Gaussian distribution, your standard normal distribution. I'll take the sample from that distribution. This is the distribution that is known to me. I can take any Z from here, give to the decoder, and decoder will give you the new image. And you know that in this distribution, you are having infinite amount of, you can generate infinite amount of Z. So now this is not only your data set. Now you learn the distribution. Now you know the distribution. Take any sample from this, give to the D, and get the image. Hey, did you get this thing?
Yes, sir.
Yes,
Any
sir.
Yes,
question?
sir. Yes, sir.
But this is like the best case. But in worst case, maybe you maybe you'll be not able to go close to the normal. Okay, so it depends on that, like how complex the problem is. Suppose your problem is very complex, then it will say, hey, I'll not go close to the Gaussian. Then you cannot do anything. This is just like trial and error. You train it. If the distribution of the encoder started to follow the Gaussian distribution, that means your loss got close to zero. That means that is the happier case. Now you can use Gaussian distribution for sampling out Z from that and give to the decoder. Okay, so this was the initial idea of this Variational autoencoder, and then and that was the initial, we can say, generative model, because here you can generate new image. But again, it is having a lot of it's having some issues also. Like the issue was like it was using KL divergence, and KL divergence is not symmetric. So if I say like KL divergence between this, that is not same as KL divergence between this and this. Okay, so it's like not symmetric. This is not the symmetric function. So KL divergence between A comma B is not equal to KL divergence between B comma A. So I'll not go into depth. I'm just giving the intuition. So it was, and that was the one issue. And another problem was like it was giving the some blurry image. Why? Because it was totally relying on the reconstruction. It was also relying on the reconstruction loss. So and most of the time you will be using Euclidean and like that. So that will give you some blur image. So in some in many cases it was giving the blur image. So this was the problem with the Variational autoencoder. And then for solving this problem, GANs came into the picture, generative adversarial model, generative adversarial network, and it has used JS divergence that is like symmetric. So and the second thing is that in the GAN they have not used reconstruction loss. They have removed the reconstruction loss. Instead, they have used cross entropy loss every time. So and due to that, GAN has given better reconstruction, better generation compared to the this Variational autoencoder. And nowadays we are also having some other new architectures, new type of models like diffusion model or maybe some other type of new model. So these are like maybe you might have heard of stable diffusion and all those new type of architecture. So like text to image. So those are like based on some type of generative model only. But you are having different options. Could go with a Variational autoencoder, but it's having some limitations. Then GANs is also there. Then again nowadays diffusion model is also there. So these are the different type of generative models which are being used for generating new images. So I'll not go into now in this part because this is not the part of our course. So we have like more or less we have completed the deep learning syllabus. Okay, so almost all the chapters. So I'll stop here and uh, in the next class, like after lunch, maybe I'll take the demo. So our course is completed. So if you guys, if you need like some, because last time you were saying that you need maybe one brief summary of this whole syllabus. So if that is required, then maybe I'll be taking that in the next week. Otherwise, our course is complete. So I'll stop here only right now. 0.2. Thank you. Okay, so we'll meet 2:30.